Maxwell's equations. Electromagnetic. In the electric field E, and the magnetic field B, a charge Q will experience a force, the Lorentz force. F equals QE plus V times B. Static charges produces E fields and moving charges produces B fields. Maxwell's equations. Electromagnetic. The effects may be summarized in the expressions for the divergence and the curl of E and B. Div equals slash. Curl equals 0. Div B equals 0. Curl B equals mu0 J. Maxwell's equations. Electromagnetic. Equations without divergence and curl express passive aspects, while with curl and divergence express active aspects. A field with a curl but no divergence is called a solenoidal field, while one with a divergence but no curl is called an irrotational field. Electrostatic field potential distribution. Equipotentials in electric field vectors of electrostatic field. Equipotentials in electric field vectors of electrostatic field. Electric field vectors. Equipotentials in electric field vectors of a microstrip line. Potential distribution. Potential distribution associated with a corner resistor. Electric field magnitude. Logarithmic scaled electric field magnitude. Electrodynamics. F equals E, a charged particle. If a charged particle is set free in an electric field, it is accelerated by a force proportional to the field and charged particle. F equals E, where F is force, E is a charge, and E is electric field intensity. Electrodynamics. dmv dv dmf equals m plus v dt 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 Newton's second law, where m equals mass of particle, kg. V equals velocity of particle, m1. Electrodynamics. F equals m dv equals ma dt ma equals E. Newton's second law. F equals m dv equals ma dt ma equals E. Velocity is very small as compared to velocity of light. Mass is essentially constant. Electrodynamics. W equals m a dl equals E, dl W equals mv dv equals ev. Energy. Integrating the force over the distance traveled by charged particle is 2 W equals m a dl equals E, dl 1 while the integral of E between points of 1 and 2 is a potential difference V. 2 W equals mv dv equals ev 1 W equals half a meter V22 V12 equals ev. Electrodynamics. W equals ev equals half mv2 particle energy, where W equals energy acquired by particle, J. V2 equals velocity of particle at point 2, or final velocity, ms1. V1 equals velocity of particle at point 1, or initial velocity, ms1. E equals charge on particle, c. M equals mass of particle, kg. V equals magnitude of potential difference between points 1 and 2, v. Electrodynamics equals 2 electron volts / m. Final velocity. Considering a charged particle E starting from rest and passing through a potential of v, will attain the final velocity of equals 2 electron volts / m. M equals mass of 0.91 by 10 to 30 kilograms, will attain velocity equals v equals 5.9 by 105 v. Electrodynamics. Final velocity. While E equals 1.6 by 1019 c falling through, V equals 1 volt. Energy equals 1.6 by 10 to 19 joules. m equals mass of 0.91 by 10 to 30 kilograms, will attain velocity equals v equals 5.9 by 105 v. At 1 volt the charge attains 590 kilometers 1. Electrodynamics A equals EVD EVDL, V equals Et equals MTM VXTV, equals tan 1 VXL. Ed. Vx. D. Electrodynamics problem, as T with Vi equals 1500 volts. Deflecting space D equals 10 mm. Deflecting plate length equals 10 mm. Distance x equals 300 mm. Find Vd to deflection of 10 mm. Deflection y equals VDLx/2 VAD. Vd equals 2 VAD/Lx equals 100 V. Electrodynamics dF equals IXPDL, N, motor equation I equals Qt. Moving particle in static magnetic field. Force on a current element dl in a magnetic field is given by dF equals IXPDL, N, motor equation. I equals Qt. EL equals QL/T equals QV. Idle equals dQV. dF equals dQVXB. F equals EVXB, Lorentz force. Moving conductor in a magnetic field. Electrodynamics. Moving conductor in a magnetic field. E equals FE equals VXB. V12 equals E, DL equals VXB, DL. 2 2 1 1 1. Generating equation. B DL V two E equals VXB, electrodynamics. Magnetic brake. Electrodynamics magnetic brake. I, B, and push. Therefore F2 to I is opposing to push. Conductive plate. Magnet assembly. Electrodynamics. Magnetic levitation. How does the levitron diaresis work? When the top is spinning, the torque acts gyroscopically and the axis does not overturn but rotates about the, nearly vertical, direction of the magnetic field. How does the levitron diaresis work? Levitation. Electrodynamics. Levitation. Electrodynamics. Levitation. We may perhaps learn to deprive large masses of their gravity and give them absolute levity, for the sake of easy transport. Benjamin Franklin. Electrodynamics. Maglev trains. Electrodynamics maglev train. A maglev train floats about 10 mm above the guideway on a magnetic field. It is propelled by the guideway itself rather than an onboard engine by changing magnetic fields. See right. Once the train is pulled into the next section, the magnetism switches so that the train is pulled on again. The electromagnets run the length of the guideway. Electrodynamics. Maglev train track. Maglev train. Aerodynamics brakes.